Algebra 2, Chapter 13, Test Review, Exponential Functions. This is going to be I hope, not too long of test review that will prepare us for our forthcoming test. So we'll go over these problems. A car that cost $20,300 is decreasing in value at a rate of 15% each year. Write an exponential decay function based on this situation. So we'll do that first. What we have is the function is going to take the form, and we've done this in classes. You have a of t, or your amount at time t, is equal to your starting amount, we'll call p sub 0, times 1 plus r to the power of t. So this is the simple interest problem. And here we have r is equal to 15%. But for an equation that we're going to use in our formula, we need to have a decimalized version of that, which is going to be 0.15%, or 0.15. And since we're decreasing by 15%, that's actually going to be minus 15% and minus or negative 0.15. So the function is going to be this: a of t is equal to our starting amount, p sub 0. So p sub 0 is equal to this 20,300. So 20,300. And we have 1 plus r, and r is going to be negative 0.15 to the power of t. And so, combining like terms, we have a of t is equal to 20,300 times 0.85 to the power of t. And t is going to be equal, so t equals time in years. So we've done that. That's going to be that part of the problem. And then use your function to determine when the value of the car will be $4,000 to the nearest year. So what we're going to do is put an equation in our calculator, our TI 84C calculator, where that's going to be y equals 20,300 times 0.85 to the power of x. And we'll see this in our calculator here. So we go to y equals, we put in 20,300 times 0.85 to the power of x. So now we have an equation. So we can graph this in our calculator. We need to get our window right for that. And we're going to assume that maybe 10 years is okay, 0 to 10. And then as far as the y value, we can go up to, I think we have $20,300. So I'll go to 22,000. And we're going to go up by thousands. And so when we graph, we should get, yeah, this will be just fine. We want to find when we're $4,000. I hope that's long. I hope that's big enough. Let me check here. Well, what I'm going to do is go to the grid, second format. I'm going to go to grid line. And we enter that and graph. So we're up by thousands here, so these grids are 4,000, 1, 2, 3, 4. So it looks like might be year 10, but we can find that. We can trace. That's one way to do it. If we go to trace, we can trace to the right. We want, what is the value of the car equal to, or approximately $4,000. So coming back here. We're coming down in value. So when are we going to get to $4,000? Looks like right about x equals 10. And we can go to, let me change my window here a little bit. I'll put it out to 12 graph. We can get it even more exactly if we go to y equals and put in 4,000 right here. Graph. And we can go to second trace 5. Enter, enter, enter. So yeah, 9.99 years. So that'd be 10 years, we will say. So 10 years will be our answer to that. So that's problem 1. Problem 2, will the transformation of f of x equals b to the x power of x change the function's end behavior when the function is translated horizontally? So if we have a function graphed, an exponential function graphed on a xy coordinate plane, we have here we have it right like it looks something like this, right? And when we translate this horizontal, we have our end behavior in place. We can see our end behavior as x approaches infinity, f of x approaches infinity. As f of x approaches negative infinity, f of x approaches 0. And so when we translate this thing left or right, does that change the end behavior of this function? No, it does not. So answer, no. Reflected across the x-axis. Let's reflect this across the x-axis. Okay, we come here and flip up, down. There, this is flipped. Now we've reflected across the x-axis. Have we changed the end behavior? Yes. Why is that? Because as x approaches infinity, f of x approaches negative infinity. So yes, end behavior is changed as if we reflect the exponential function about the x-axis. Next, for h of x equals negative 1/3 times 4 to the power of x plus 2 plus 3, what are the domain and range of the function? Well, the domain is going to be in set notation all real numbers. X such that x is an element of all real numbers. Or in interval notation, we could write that as greater than negative infinity to less than infinity. And what about the range? Well, the range is going to be one of two possibilities. If we have an upward opening function, what we have, and I'm going to put this interval notation, we are going to be, our range is going to be from greater than k to less than infinity. That's for upward or increasing functions. Where a is greater than, well, actually it's going, the function will be going down, will be above the asymptote. But for downward functions, what we're going to have is the range could be from negative infinity to k. For downward, or below, we'll just say below below the horizontal asymptote. Horizontal asymptote functions. Okay, now this function here, is this going to be above or below? Well, this negative means we're going to be below k, and k is equal to 3. So in this case, we're going to have our range is going to be in set notation y such that y is going to be less than k or 3. Or in interval notation, we're going to have greater than negative infinity up to but not including our value of k, which is 3. So that's going to be our range in our domain, and that's our sample problem 3. Next, graph the function h of x equals negative 1/3 times 4 to the power of x plus 2 plus 3, labeling the new values of reference points and the asymptote. So we're going to look at our parent function is going to be f of x equals 4 to the power of x. And for our reference points, we're going to use the input values of 0 and 1. And if we input 0, 4 to the power of 0 is 1, and 1, the next reference point, 1 to the power, or 4 to the power of 1 is 4. So those are going to be our reference points. And then as far as our asymptote goes, we have k, so k is equal to 3. So that's going to be the value of our horizontal asymptote. So I'm just drawing the dotted line here. So I'll put y is equal to 3. And let's go ahead and trace our reference points. I'm going to do that over to the left. And we're going to start with 0, 1, and right below it 1, 4. We did quite a few of these in class. The first thing we're going to do is reflect about the x-axis. So reflect, put up here, reflect x-axis. And for that, what we do is we take our coordinate pairs and we change the signs of the y value. So instead of 0, 1, we have 0, negative 1. Instead of 1, 4, we have 1, negative 4. Okay, the next thing we're going to do is take our translation, and so what we have is h, if we have x plus 2, h is equal to negative 2, because x minus negative 2 is x plus 2. So we're going to translate 2 units to the left. So I'll put here 2 units left. And so for that, what we do is we take the x values and subtract 2 from them. So we have 0 minus 2, or negative 2, and then we bring over this negative 1, and we have 1 minus 2, or negative 1. So now we have gone 2 units left. The next thing we're going to do is take our value of k, and we're going to go 3 units up. Okay, and what we do for that is we add 3 to the y value. So we have -2, comma, and -1 plus 3 is going to be 2. And then we have -1, and -4 plus 3 is -1. So now we have our new values here. And I'm going to put these on our coordinate grid. So I'm going to put -2, 2 right here. And I'm going to put -1, -1. So -1, -1. So what this is going to mean is our graph is going to be like this. Now, it's not really going to be like this, because the last thing we have to do is, and I kind of ran out of room here, I'm going to say vertical stretch. Let me get my skinny pen back again. We'll say a vertical stretch by factor of 1/3. And what we're doing is we're looking at the horizontal asymptote and going 1/3 of that distance. So here we are at this first one right here. Actually, that's going to be -2. Yeah, the first one here, we have an input value of -2, and then we take the second value of 2 and go with 1/3 of the distance to the horizontal asymptote. So that's going to be 2 2/3. So I'll say, I'm writing mix number 2 2/3. So that's going to be right here, drawing that in blue. For the next one, we're going to have -1, and that point's going to be 1/3 of the distance to the horizontal asymptote, and we're 4 away. So we have to take, so 4 divided by 3 is going to be 4/3. So what we have to do is take this 3 minus 4/3, which is going to be 1 2/3. At 1 2/3, so it's going to be about right here, which is 1/3 of the distance to the horizontal asymptote. So our graph is going to look like, oh, let me get a different color. The graph is going to look like this. If I could draw it right, it'll come like this. Yeah, it looks something like that. So let's put that right here. So 1 2/3, we'll call that. So that's going to be it, new values of reference points. These are the new values right here. Okay, let's go on to the next problem 5. A lab sample in a petri dish starts out with 200 cells. The cells increase in number by a rate of 21% per day. Find the function that models the situation. Well, again, we're talking about this one right here. A of t is equal to p sub 0, which is our starting amount, our population, times 1 plus r to the power of t. And here we have a rate of 21% per day, so r is equal to 21%, and we're increasing, so that's positive. And in decimal form, that's going to be 0.21. So our function is going to be a of t is equal to our starting amount, which is 200 cells, 200 p sub 0, and we have 1 plus 0.21 to the power of t, and t in this case is equal to days. And so just simplifying here, a of t is equal to 200 times 1.21 to the power of t. So that's going to be our function that models the situation. How long will it take the population of cells to quadruple in number? Well, quadruple is going to be 200 times 4, which equals 800. So we can rewrite this function as 800 equals 200 times 1.21 to the power of 1.21 to the power of t. And we could do this a number of different ways. The way I'm going to do this now is by graphing. I'm going to put y1 in the calculator equals 200 times 1.21 to the power of x, and y2 is going to be equal to 800. And we will find out when that happens. We'll go to the calculator. I'm going to put 200 times 1.21 to the power of x, and then up here I'm going to put 800. I need to change that window. X max I'm going to leave the same at x max of 12. Y max I'm going to make 1,000 because I know I need to get to 800. I'm going to go by 100s. And then graphing, this is what we're looking like. So define our intersection point, second, trace, 5, enter, enter, enter. And so we have 7.27, 7.273 we'll call it. X, or that's going to be t, right? T equals 7.273, and that's going to be days. And then to the nearest tenth, that's going to be 7.3 days, which is going to be our answer. Next, problem 6. Compared to the graph of f(x) equals 1/2 the power of x, what are the graphical transformations of f of x to produce g of x equals 2/3 times 1/2 the power of x plus 2 minus 4? Well, we'll say that g of x is f of x. We'll have translated. Well, I think I'll do the compression first. Vertically, are we compressing or stretching? We're vertically compressing. By a factor of 2/3. And also g of x is translated which way? We have x plus 2, which x minus h, so we have to have h equal to -2, so 2 units to the left. well, actually it's f of x is translated. F of x is, I'll make sure we have the right letters here. F of x is translated 2 units to the left, and we have k is equal to -4 and 4 units down. So that's it. That's our answer. Next, 7. Write the function represented by the graph and state the domain and range using set notation. And I don't know how visible it is here. We can kind of see, we can see the graphics pretty well. We appear to have a horizontal asymptote here at y equals 1. So horizontal asymptote, y is equal to 1. And so we have our exponential function, that's the value of k. K is going to be equal to 1. Now, our reference points are going to be these. Okay, we're going to have x, f of x. We're going to have -1 and 0 for our decay functions, and for 0 our f of x is 1. For -1 we don't know what that is yet, but what happens, this point here 0, 1 has come over here to become -2, 5/3. So h is going to be equal to -2. So we're going to start writing this equation or function with this point. So it's going to be f of x is equal to a times b to the power of x minus -2, or x plus 2, and then we have out here our value of k plus 1. And we're going to use our first point, which is -2, 5/3. So using that first point, 5/3 is equal to a times b to the power of -2 plus 2, and then plus 1. And so b to the power of -2 plus 2, that's going to be 1. So what we get is 5/3 is equal to a plus 1, and I'm going to write 1 in thirds, so that's going to be plus 3/3. And if we subtract 3/3 from both sides of this equation, we're going to get a is equal to 2/3. Now, what I'm going to do is come up here and use our second point. I'm going to write this now as f of x is equal to, we know what a is now, which is 2/3. So 2/3 times b to the power of x plus 2 and then plus 1. And now we're going to use the values in the point here, which are going to be 3 is equal to 2/3, and we have b to the power of -3 plus 2. Let me make that a little more legible if I can. We'll put -3 plus 2, and then outside here plus 1. And what we have here is 3 is equal to 2/3, and we have b to the -1 power (2/3) b to the -1 power plus 1. And what that's going to be is, well, we'll subtract 1 first. So we have 2 is equal to 2/3 b to the negative 1 power. And just working to the right here, this b to the negative 1 power is going to be down in the denominator b to the 1 power. So we get 2 is equal to 2 over 3b. And if we cross multiply 3b, I'm going to continue to work to the right. 3b times 2 cross multiplying, we get 6b is equal to 2. And dividing by 6, b is equal to 2 over 6, or 1/3. So our final function is going to be, I'm going to write this right below. We'll say f of x is equal to a, and a is 2/3, b, and b is 1/3, to the power of x, that's going to be plus 2, and then out here we're going to put plus 1. So I'm going to go ahead and graph and to see if that's correct, and for that we'll go into our calculator. Okay, 2/3. So we have 2/3 times 1/3. I'll put times 1/3. Let me go ahead and parenthesize that first. I'll go like this. We'll say 1/3 to the power of x plus 2, and then we're going to say here plus 1. Now I'm going to go to zoom 6 to get a standard window here. So this is what it looks like. Or make sure we have the points that are the same. If we go to table view, second graph, we should get, okay, we get -2 5/3 and -3 3. So those will check out. So this is a good function right here. And domain and range, set notation, I'll say domain is going to be x such that x is an element of all real numbers, and range is going to be y such that y is greater than k, which is 1. Okay, next, 8. Given the exponential function f of t equals 3 times 0.8 to the power of t, find the average rate of change from x equals 0 to x equals 6. So what we're going to have, our average rate of change, I'm going to put average ROC equals f of b minus f of a over b minus a. And b is going to be defined as our final amount. So we'll say b is equal to 6, and our starting amount is a, and a is equal to 0. So what we're going to do is plug in our values. So if we plug in f of 0 and plug in 0 for that, we get 3 times 0.85 to the power of 0, which is going to be 3 times 1, or 3. So that's going to be f of 0, f of 6 is going to be 3 times 0.85 to the power of 6. And we will find out what that is shortly. Three times 0.85 to the power of 6. So we have this number here. I'm going to go out to like 1.1314. I'll call that. That's out to the 10,000ths place. So average rate of change is going to be equal to, I'll put approximately now, f of b, which is 1.1314 minus f of a, which is 3 over b minus a, or 6 minus 0. So let's go to our calculator. I'm going to get this fraction, f of b, that's going to be this figure right here. So I'm going to put second a and s, and we're going to have minus f of a, which is 3, over 6 minus 0. And this is going to be it. So we get negative 0.3314. 0.3314. And it doesn't give any units. A lot of times you'll say feet per second or something like that, but this is as close as we can get it. Now the last problem in this set is one where you have the town of Silver Springs has a population of 5,000 at the beginning of 1990 and grew at an exponential rate to 12,000 at the beginning of 2020. The exponential growth function that models this situation is this one right here. P of t equals p sub 0 e to the 0.029,182 t, where p sub 0 is the initial population. Okay, this one here takes the form of a continuous compounding formula. That's going to be a of t, we'll call that, equals p sub 0 times e to the power of r, the rate, times the time. Okay, let's see. To determine after what year the population will be 20,000. Well, and that says what is the growth rate of the function. I'm going to get the growth rate first. R is equal to 0.029,182, or this will be 2.9182%. Okay, so that's the answer to the second part. Determine after what year the population will be 20,000. Well, we can use this equation right here. P of t, we'll call that 20,000, equals our starting population of 5,000 times e to the power of 0.029,182 t. And what we can do is enter this in the calculator as y1 equals 5,000 e to the 0.2029 182 x, and y2 we can let equal to 20,000, no, 12,000. What am I putting 20,000 there for? Can't even read my own typing. I want to say read my own writing. That's typing. So that's going to be 12,000. Or 3 times. There we go. 12,000. So let's go to the calculator. Go here. And I'm going to put in 5,000 times E second. E to the power of 0.029. Let me make sure I get this right here. 0.029, 182. 182x. And then we're going to have, down here we're going to put 12,000. Adjust that window. Let's see. Here's the window. We're going to go from 0, say, to, I don't know how many years it's going to be. We'll say 30 years, in case it takes that long. And we're going to go up to, we need to go to 12,000. I'm going to put 15,000 here by 1,000s. And we graph, and this is what we see. Ooh, we're just barely hitting it here. So 30 years was almost not quite enough, so I'll make this 35. So second trace 5. Enter, enter, enter. So we get, yeah, 30, exactly 30 years. So 30.000299. So we would say T is well, wait a second. We do want to go to 20,000, don't we? Determine after what year the population will be 20,000. Yeah, I was reading 2 different, so I'm going to change again. 20,000. Okay, we could have to change that again. I'm going to have to increase the time here. Okay, window. I'm going to go to 50 years. I hope this works. Yeah, it's going to work. Oops, but I don't have my window adjusted high enough for Y, do I? Let me go to 22,000. Now it should work. Ooh, okay. Second trace 5. Enter, enter, enter. So T equals about 47.5 years, we'll call it. We'll say 47.5 years, about. And it says, determine after what year the population will be 20,000. So what we'll have is, we're going to have 1990 plus 47.5 years. So that's going to be 0.5, 7, 13. So 2037, after year, we'll say after year 2037. So right after year 2037, that will be when we'll have a population of 20,000. So that's going to be the whole review we have. Just going to be these types of problems. This should be helpful to you. Good luck, and thanks for viewing.